All right, now that we've gone over some basic things about the probabilistic method, we're ready to now prove our claim that r of tt is greater than 2 to the power of t over 2. So what we're going to do, as stated previously, is we're going to show that there is some red-blue coloring of Kr that does not contain a red or blue Kt by showing that the probability of such a thing happening is that there is some coloring that doesn't contain a red or blue Kt, showing specifically that the probability that a given graph doesn't have a red or blue Kt, we're going to show that probability is greater than 0. So recall we're going to let our probability space S be the red-blue colorings of Kr, with each coloring appearing with equal probability and remember that was going to be given by 1 over 2 to the power of r choose 2, which is the same as something like 1/2 to the power of r choose 2. So that's the probability of one of these colorings appearing. And we're going to let A be the event of, we're going to let A be the event of having no red or blue Kt, and we want to start by finding not the probability of A, but the probability of the complement of A. That is the probability of finding, or the probability of having at least one copy of a red or blue Kt. To do so, we're going to sum over the probability of any T element subset vertex subset of Kr being all the same color. I'll just say being a red or blue Kt. So just for a simple example, even though we're going to be dealing with numbers much bigger than 5, what we're basically going to do is I'm going to check what's the probability of, let's say we're looking for t equals 3. Let's check the probability, is this a red K3 or a blue K3? Or maybe, is this a red or blue K3? Or is this a red or blue K3? Or is this a red or blue K3? And basically, I would find the probabilities of all of those. And as we said earlier, the probability of this or this or this happening is at most the probability, the sum of their individual probabilities. So we're going to write out a lot of what that is soon. But first, let's just examine the first question. So we're summing over the probabilities of a T element vertex subset of Kr being a red or blue Kt. For any such subset, we'll call it T. Let AT be the event that it's monochromatic. This should be a capital T. Let AT be the event that t is a red or blue kt. What's the probability of that happening? Well, each edge is colored independently, and each one has a 50-50 chance of being one color. We could ask, what's the chance that all the edges are red? So the chance that all the edges are red, that's going to be 1/2 the chance that any individual edge is red to the power of t over 2, the number of edges in between those t vertices. Similarly, if all the edges are blue, that's going to have a probability of 1/2 to the power of t choose 2. So the probability that probability of AT, and note that these are independent events, so the probability of AT is going to be exactly the sum of these two probabilities. Okay, I shouldn't have said independent, because that's the wrong thing. These are mutually exclusive. I can't be both all red and all blue. So I'm going to add these together. So it's going to be 1/2 to the power of t choose 2 plus 1/2 to the power of t choose 2. And there's a nice special way to write that. You can write that as 2 times 1/2 to the power of t choose 2. And then if you're feeling really special, you could write that as something like 2 times 2 to the negative t choose 2. Which is the same as 2 to the power of 1 minus t choose 2. So that's for any given subset. And now we're going to let cursive t be the set of all t element subsets. Then let A of cursive t, well, actually, we don't even need to name it that. Then the probability of the complement of A, which is what we're interested in right now, is going to be less than or equal to the sum for all t in this cursive t of the probabilities of A of t. And why is that? Because this A is the probability of any set being, or is the probability of there just being some monochromatic triangle, or not triangle, but some monochromatic red or blue KT. And here we looked at all the individual cases where a given set of vertices was a red or blue KT. So we're basically just summing over all the different sets of T vertices. And by doing that, we're going to get the probability, or at least an upper bound on the probability of having at least one red or blue KT. So we don't even need to write let there. That's what that's going to be. And we just calculated what A of t was. So that's going to be 2 to the power of 1 minus t choose 2. And how many things are there in T? That's the number of T element subsets of our vertex set. That's going to be R choose T. Let's go ahead and do a little bit of rearranging there. R choose T is going to be the same as R factorial over T factorial, R minus T factorial. 2 to the power of 1 minus 2 choose T. And one thing you can note is that R factorial is going to be well, specifically r factorial over r minus t factorial. That's going to be something like r times r minus 1 times all the way up to r minus t plus 1. And there's like t of these terms. So that's clearly going to be less than r times all the way up to rt times, which is r to the t. If you want a nice combinatorial explanation of this, this is basically the number of ordered subsets, and this would be basically sequence order matters, repetition isn't allowed, and we're saying that the number of things where order matters and repetition isn't allowed is less than the number of things where order matters and repetition is allowed. So because if I'm allowed repetition, I could just choose not to repeat things. So, that's a nice combinatorial justification for that inequality. So we'll go ahead and use it here and turn that into r to the t over t factorial r minus, not r minus t factorial, just t factorial. 2 to the power of 1 minus 2 choose 2. Okay, we need to give ourselves a little bit more room here. We're getting there. So we have this inequality, and this is going to be magical for us. Why is it going to be magical? Well, note that since r equals the floor of 2 to the t over 2, which is clearly less than just 2 to the t over 2 without the floor, then r to the t is going to be less than or equal to 2 to the t squared over 2. Interesting. So let's go ahead and use that. So we now have that p of the complement of a is going to be less than, let's start with what we had. We had r to the t over t factorial, 2 to the power of 1 minus 2 choose 2, which is less than or equal to 2 to the power of t squared over 2 over t factorial times 2 to the power of 1 minus t choose 2. And let's go ahead and pull out our fancy-dancy inequality from earlier. That's going to be less than 1/2 t factorial 2 to the power of t choose 2 times, or over t factorial. That's not a factorial. What am I doing? Times 2 to the power of 1 minus 2 choose 2. And let's do some clever things. This here looks like that's probably 2 to the negative 1. Cool. I see those t factorials are going to cancel. So this is really 2 to the power of t choose 2 minus 1 times 2 to the power of 1 minus t choose 2. And that's all going to cancel out to be, we'll say, 2 to the power t choose 2 minus 1 plus 1 minus t choose 2, which equals 1. So all that says that p of a complement, the probability that there's at least one red or blue KT is less than 1. This means that the probability of our original event that there's no red or blue KT is going to be equal to 1 minus the probability of A, which we just showed this is less than 1, so this has to be greater than 1 minus 1. In fact, I'll write it like that. This has to be greater than 1 minus 1 equals 0. So what does that mean? That means the event A, where there is no red or blue KT is non-empty, which means some red or blue coloring, or some red-blue coloring of Kr has no red or blue KT. Thus, we can say that R of TT is strictly less than, or is strictly greater than the floor of 2 to the power of T over 2. There we go. So we proved that there must be some red-blue coloring of Kr that has no red or blue KT just by proving that the probability that there was at least one red or blue KT was less than 1. So we said that it's not a certainty that we get a red or blue KT, which means that it has to be at least a possibility that I don't get a red or blue KT. And that's enough to say that the Ramsey number, which is the minimum number of vertices I need to guarantee a red or blue KT, that had to be at least the floor of 2 to the power of T over 2. So there's how you can use probability to prove a claim in graph theory and combinatorics.